Okay, can I start? Yeah. My name is Zhou. I'm a PhD candidate at Cornell University. So I'm going to talk about my experiences predicting ambulance demand. This is very different from the previous talks. So in this talk, I'm going to focus on one city, Toronto, Canada. We've done this for many other cities, including in Australia, Melbourne, but for now, Toronto. And the industry would like a prediction for every hour and every 1 square kilometer region, which is about a 10-city block by 10-city block. And this is needed, this fine resolution is needed because of the need for accurate dynamic deployment. And this gives rise to several challenges. Number one, data sparsity. We have lots of data altogether. This is probably 1 year of data. This is 500,000. Each point corresponds to the actual location of where this ambulance is demanded, this high priority ambulance is demanded. But if you were to zoom into a typical 1 hour period, you have 23 points. And they're scattered all over Toronto, and there are thousands of 1 square kilometer regions. So you're looking at mostly zeros. And given this sparsity, it's very difficult to detect or model patterns in time or space. But you have to zoom in to this because ideally you would like to give as personalized as possible a prediction. Challenge number two, there are some pretty complicated spatial temporal patterns. Right? Even before us, people have discovered that ambulance demand has weekly seasonality, very strong weekly seasonality. And we confirmed that for Toronto, but that's not the end of the story. For example, downtown Toronto, which is in the box here, it also has very strong daily seasonality and short-term serial dependence. But at some other places, probably more dispersed, such patterns were not as pronounced. So your set of patterns were changing depending on locations. So that's challenge number two. So up to this point, the industry has one practice. Let me use the example of the so-called magic method. So to predict this day that I've circled here in red, it's a Wednesday. And let's say I want to predict for 1 to 2 o'clock in the afternoon. For that task, the industry would look back in time for 8 prior 1 hour period. Right, same Wednesday, same 1 to 2 o'clock in the afternoon for the 4 preceding weeks, as well as the same 4 weeks in the preceding year. And then you grid Toronto up into these 1 square kilometer regions that have 8 of these count pictures. Right? The green means 0 mostly, and then most of this red means count of 1. And then your ultimate prediction is the average of these 8 pictures shown down here. This, unfortunately, is the state of the art in the industry, with very small differences from city to city. As you can see, this is a very noisy prediction. Most of the cells are 0. And the major problem is that if you can imagine this sequence of his future predictions, a lot of these cells would flicker from 0 to 1, 0 to 1 all the time, causing a lot of inefficiency in dynamic deployment. Right? So this is where we want to improve things. Right. The first thing that we thought of is maybe we should predict demand continuously in time so as to lessen this impact of discretization. Right. Along these lines, we made 2 assumptions. Firstly, demand locations at each time follows a non-homogeneous Poisson process because it's a continuous space with intensity function lambda sub t. Right. So that you can visualize this lambda sub t as a 2D surface defined on the map of Toronto that is governing the rate at which ambulance demand happens. So you have a different 2D surface per time. Right? Second assumption, lambda equals to delta times f. Right? Delta is what we call the aggregate intensity that's used to model how many calls that I'm going to get from anywhere in Toronto. Right? And f is then a normalized spatial distribution of where exactly those calls are coming from. Right, so this delta problem is much simpler. It doesn't have space. It's a single time series. Many methods has been proposed, including singular value decomposition factor models, ARIMA, time series models, etc. Pretty good accuracy has been achieved. But this F is an entirely different story. Apart from the industry method, somebody, I think this Setzler et al. Used neural nets, but it's very difficult because of the data sparsity. They did not beat the industry method. So we would like to focus on this F, right? The goal is threefold. Number one, accuracy, obviously. Number two, speed, because we have to do it every hour. Number three, interpretability, because the EMS industry, the managers would like some sort of insight as to what the patterns are going on, how are they changing in time and space. So with these 3 goals, we proposed a number of methods, out of which I'm going to talk about 2. The first method I'm going to talk about is spatial-temporal Gaussian mixture model. So then the idea is to use a Gaussian mixture model, which is really just a linear combination of a number of 2D normal distributions, to capture that F surface. But the problem is you cannot fit one such surface, one such Gaussian mixture model per time, because you only have 23 data points, right? So then the solution is that, how do we overcome that? You fix the mixture component distributions in time, and then you let the mixture weights change in time. So pictorially, let me explain this. So you're going to fix the center and the shape of each of these bumps in time. Their job is to model the city structure, the neighborhoods, the hotspots. They do not change hourly. The only thing that you allow to change over hourly are the mixture weights, which is the relative height of these bumps. Right? It indicates how people are moving, what people are doing at different times. In the end, you get different surfaces at different times. Right? So mathematically, you have, very briefly, this Gaussian density linear combination weights at the p's. Right? You can visualize this p's in the following way. Right? You can think of it as k columns here. One column corresponds to one component. And then each column is a time series, right? It's the time evolution of how hot this particular hotspot is at that particular neighborhood, right? So question number 2, how do we deal with that spatial temporal pattern, right? We have 2 methods. Number 1, very simple, constrain them. We have a very predominant weekly seasonality. Very simple solution, block the p's into weekly blocks and enforce these blocks to be repeating. That means the corresponding p's in the corresponding row and column must be the same, right? This tantamount to pooling data across weeks, right? And the second solution, what about those more subtle patterns that may or may not show up depending on locations? Then we put autoregressive priors, which really, we put a separate autoregressive prior for each of these time series of P. This prior represents our belief in what the patterns are like at that particular neighborhood. Right? So these priors could encode seasonalities, could encode serial dependence, whatever dependency structure that you like. I'm not going to go into details of this autoregressive prior, but we can talk about it offline. We use the Bayesian estimation, MC Markov-Chain Monte Carlo, to be more specific. I'm going to show you results using 15 components. In our paper, there are very involved ways of coming up what the good number of components are and how to incorporate spatial and or temporal features such as demographic information and weather information, and I also don't have time to talk about them. Let me show you the results of the bare bone. 15 components, here they are. Prediction for 2 to 4 a.m., this is in the middle of the night, and p.m. in the afternoon. You can see that the downtown is a lot, I think the color did not transport very well. There is some sort of difference. And let me remind you, this is what the industry predicted for the same time period. And performance-wise, because we have a density estimate, density forecast, we use a likelihood-based metric. It's really average log score. This is average log likelihood of all test data, right? And the higher, the better, right? So results. Gaussian mixture model, I gave a range because we had some configuration of a number of components, but it's a remarkable improvement from the MEDIC method. Right, so this first method made a lot of headways on accuracy. Speed is not bad. It's about 6 hours on this computer for an entire month of forecast. And interpretability, there are some, right? Some sort of hotspot things that you could potentially interpret. And but for the second method, we really want to drive home speed and interpretability and make it almost instantaneous without sacrificing accuracy too much. So this is the second method, spatial-temporal kernel density method. And let's go back to the question that we want to predict for this future time period named with this question mark here. Obviously, we've got to look back in time for inspiration. But where exactly do you look? The industry says, let's just focus our energy on the corresponding hour in the previous weeks. But when you think about this, this is probably an overly simplistic view of what happened, right? It's probably more like this. Each historical time period has some sort of utility. There is a general decay, and some important time periods show up because of patterns, right? And we could potentially encode this usefulness into one function, W for weight. And if we manage to get our hands on this W, then we can potentially build a model like this, right? So loop through a bunch of historical data, I going from 1 to n, to as far back as you want to look. And then you build a spatial kernel, for example, radio basis kernel, Gaussian kernel, whatever kernel you like, at where each of these historical data is, at the location of the historical data. But then you weight this kernel by the weight function, which is determined by when exactly these historical data happened. So if a historical data happened at a particular telling time, historical time, then it will contribute more so to building this F, right? So you can notice that there is a complete separation of time and space. This is an orthogonality assumption, right? And so the question is, how do I get my W? Right? We would like to model this interpretably, so therefore parametrically. And there are 3 big patterns in ambulance demand over and over again. Number 1, short-term serial dependence. What happened immediately before seems to be a good idea of what's going to happen next. So then we use this exponential decaying function, rho 1 to the L. Weekly seasonality. Rho 3 to the sine square pi L over the period of 1 week. Right? Exponentially discounted to indicate last week's information might be more important than the week before last. Third pattern, daily seasonality. Very similar story. Different parameter, different period, but otherwise the same. So the W is short-term serial dependence plus weekly seasonality times daily seasonality, all exponentially discounted. This is one choice of this W. There are probably many sensible such choices. It's mostly inspired by the covariance function of Gaussian processes. They have some nice properties. And in our experience, it worked particularly well for our data. So then the question becomes, how do we get our hands on rho 1 to rho 4? Well, you probably don't want a single set of rho 1 to rho 4 for the entire city because you have location-specific patterns. So you want a set of rho 1 to rho 4 per smaller region. And the easiest way, discretize, right, this into 20 big regions. A more sophisticated way to do this is to use triangulated area of nearby ambulance spaces, as long as you make sure you have enough data to robustly estimate rho 1 to rho 4. And then, so at this point, there are several ways to go forward. The easiest way is probably just loop through all training data, hundreds of thousands of them, maximize likelihood stochastic gradient ascent, estimate 4 times 20, 80 data point, 80 parameters. That's not exactly very fast, very instantaneous. There is a faster way to do this. Right, let's focus on this particular square here, this downtown Toronto. And remember that we're trying to get this W function. Right, this W function is trying to encode what the patterns are like, temporal patterns are like, at this particular place. There's already something that does that. In time series lingo, autocorrelation function. It's a way to measure how similar data is to its previous self. Right, so then the idea is, why don't we find rho 1 to rho 4 such that the W function will best fit the positive part of this autocorrelation function? Right, we throw away the negative part because when we want to build a prediction, we use the most similar historical data instead of the most opposite. Right, so very simple was you just minimize the L2 distance between the W function and your empirical autocorrelation function. Right, this is a much smaller problem, 4 parameters only, independently implemented per grid, and only hundreds of hourly lag in terms of data. This is very fast. And then you can do so for different places. And 2 main advantages. Number 1, fast. This is much faster than Gaussian mixture model. It's online. It's instantaneous. Number 2, interpretability. EMS managers can look at these curves and say, oh, daily seasonality doesn't seem to be like a thing over there. They can compare downtown and satellite cities. They can compare summer versus winter, this year versus last year. They can just look at these curves. right? This is what this method predicted for the same time period, 2 to 3 a.m. and 2 to 3 p.m. This is very similar to what a Gaussian mixture model gave. And performance-wise, negative 6.10, with somewhere comparable to this Gaussian mixture model, much faster, much more interpretable, much more industry-friendly, compared to a naive KDE in which you don't have that W function, you just weight everything similarly. This is quite a bit worse because showing the utility of capturing the patterns. And of course, everything beats MEDIC method. We also looked at discretized metrics. You discretize it into square kilometer regions, and you look at root mean square error, root mean square as can be residual similar order preserved. And we also did simulation study and actually dispatch ambulances, and we showed that our methods, both of these, had a dramatic 60% improve on operations performance. Thank you. That's all.
Thank you for an excellent presentation. As one of the few physicians attending here and the chair of the National Academy's Science, Medicine, Engineering MS Safety Subcommittee, I'm fascinated with your work. The one thing that's puzzling me is, given that globally 97% of ambulance transports are benign and only 3% involve any serious or potentially life-threatening event, which is always a surprise for people, how do you factor severity into, why would you hurry for a sprained ankle when your resources are ideally suited to a life-threatening event?
This study is limited to high priority only. That's why we only have 23 points per hour. But ideally, if you could classify some sort of severity based on the call, then you could model the two processes jointly, the severe and the non-severe. And there are a lot of transfer learning, such as the sort of neighborhood structure, the Gaussian mixture model, the hotspots should remain, but the weights, the height would be different for the two severity. But you can do them jointly for savings.
Thank you very much.
Yeah, thank you.
So there's a very interesting associated problem, which is a resource allocation problem. So suppose I can have money to buy 3 more ambulances. Where should I keep them, and what will that do to my distribution of wait times? And there are companies outside the health domain like Cars to Go that rent out cars by the hour, who are greatly interested in this problem. It's a bit more complicated there because the drop-off point are not necessarily emergency centers, they're arbitrary points. But they're very interested, especially in a growing population or growing usage, what happens to these cars being picked from one place and dropped off somewhere else as they add more and more cars and as the demand goes up.
Yes.
And also, as even here, you're having a growing population in Toronto. How do you model that? I saw lots of seasonality terms, but I didn't see a growth term in the equations.
Yes, of course, because actually in this Toronto's actual practice, they do have a yearly inflation term, which is a simple ratio thing, this year's population divided by last year's population. And the problem is that we only have 2 years of data, and one of the year we held out as the test data set, so we couldn't really, this is a short-term model instead of a long-term model. And this is only one small piece of the puzzle. There are separate groups that does, predicting how fast you will be able to get to a certain location at any time and any road network, and then there is the optimization, which is not what I did.
But there are a lot of dollars associated.
Yes. Yes, to try to decrease the response time from 9 minutes to 8 minutes, it's billions of dollars. Yes. Thank you.
Let's speak.